One of the main uses for differentiation is that it lets us find where the maximum and minimum points on curves are. If we look at this curve, where the red line is supposed to indicate the tangent to a curve at a particular point, you can see that as we move along and look at different points, then that gradient of that tangent is changing. And look, as we get very close to the top of the curve, that tangent is almost level. In fact, when we get to the top of the curve, it really is level. It's horizontal. It's got a gradient of 0. If we move a bit further along the curve, the gradient changes again. In this case it's heading downwards now, so it's got a negative gradient. More and more pronounced as we move away. But what happens as we head towards this minimum point at the bottom of the curve? Well, as we get closer and closer to that minimum point, again the gradient starts to level off. The tangent is getting nearly horizontal. When we get to the minimum point, it is horizontal. Once again, the gradient of the tangent is 0. Once we move past that point, we move into positive gradients again, in particular non-zero ones. Well, what can we do with all this? We have spent some time working out how to deal with the gradients of curves. That's what we have been calling dy dx. So at these maximum and minimum points, the value of dy dx is 0. Now these points, these maxima and minimum, we call them stationary points. Stationary points. Sometimes called turning points. Stationary points is a better word for them if we can try and remember to use that. Let's look at an example. Suppose we have the curve y equals x cubed plus x squared, subtract 8x plus 2. And we are interested in where the stationary points on that curve are. Well, the first thing we will have to do is differentiate the curve to find dy dx. That is 3x squared plus 2x subtract 8. And if we are interested in finding the stationary points, we have to find where the gradient of the curve, where dy dx is 0. So if dy dx is 0, that's the same thing as saying that 3x squared plus 2x subtract 8 is 0. And I think we'll find in this case that this curve does factorise. In fact, a little bit of thought shows us that it factorises into 3x subtract 4, x plus 2. Let's just check that. 3x times x, there's the 3x squared. 3x times 2 is 6x, but then we're subtracting 4x's, giving us just 2x. And finally the negative 4 and the 2 give us the negative 8. So in this case then, we know that if dy dx is 0, then either the x coordinate is 4 over 3, or the x coordinate is negative 2. And in each case we can then go back to the original equation, the y equation, and find out what the value of y is. In the first case, the value of y will be 4 over 3 cubed plus 4 over 3 squared, subtract 8 lots of 4 over 3 plus 2. In the second case, the value will be negative 2 cubed plus negative 2 squared, subtract 8 lots of negative 2 plus 2. If we were to work those values out, we would find that in the first case we get the slightly horrific value of negative 122 over 27, and the second case we get the value of 14. Let me reassure you, you wouldn't be given such a horrible number to deal with if it were a non-calculator paper. They would design the questions so they come out quite nicely. But in this case, we have found that there are two stationary points. There's one with an x-coordinate of 4 over 3, which has a corresponding y-coordinate of negative 122 over 27, and there is also a point with an x-coordinate of negative 2 and a y-coordinate of 14. We've therefore found the maxima and minima points on that curve. Now admittedly we don't actually know yet which one is the maximum, which one is the minimum, or maybe they're both maximum or maybe they're both minimum. Well, there are reasons why those last two cases don't actually make sense, and it can't be any of those, but we shall see that it could be either of the first two situations. We'll analyse exactly how to work that out later on. One final point I want to make before leaving this discussion of stationary points. There is one other situation we can have which we haven't discussed. There's a kind of curve you can make, and let's look at the classic example, which is y equals x cubed, where that curve sort of comes up towards the axis and sort of levels off, and then goes up. I'm sure it's a terrible drawing, that's supposed to be the origin. But you can see in this case the gradient is reducing and sort of becomes zero just at this point and then goes up again. So just because dy dx is zero, it doesn't necessarily mean that you have a maximum or a minimum. This is called a point of inflection, and it also counts as a stationary point. But they are more unusual, and the chances are that normally we'll be dealing with maxima and minima.